In some process, the temperature of a substance depends on its enthalpy as, as T equals to A into S to the power n, where A and n are constant. Find the corresponding heat capacity C of the substance as a function of S. At what condition is C is less than 0. The given temperature of the substance depends upon entropy and given by T equals to A into S to the power n, where A and n are constant. Differentiating the equation, dt equals to A into n into S to the power n minus 1 into ds. Now we know that dq equals to T ds and also dq equals to m into C into dt. Hence m into C dt equals to T ds. So from 1 m into C dt equals to T into dt y a into n into S to the power n minus 1. So C equals to T by m into A into n into S to the power n minus 1 equals to S to the power n by n into S to the power n minus 1 equals to S to the power n minus of under bracket n minus 1 by m into n, or C equals to S by m into n. So for 1 kg of mass, C equals to S by n. When n is less than 0, the C will be less than 0. Find the temperature T as a function of the entropy S of a substance for a polytropic process in which the heat capacity of the substance equals C. The entropy of the substance is known to be equal to S naught at temperature T naught. Draw the approximate plot of Ts for C greater than 0 and for C less than 0. Solution: since the process is polytropic, the specific heat capacity is given as C. From the definition of entropy, dq equals to T ds. We know that dq equals to m into C into dt, hence m into C dt by T equals to ds. On integration, m into C into integration T naught to T dt by T equals to integration S naught to S ds. This implies m into C into log T by T naught equals to S minus S naught. For the 1 kg of substance, C into log T by T naught equals to S minus S naught, or log T by T naught equals to S minus S naught by C. This implies T by T naught equals to e to the power under bracket S minus S naught by C. Hence T equals to T naught into e to the power under bracket S minus S naught by C. Now for the plots A, when C is less than 0 and S equals to 0 and C is less than 0, hence T equals to T naught e to the power minus S naught by C, and the function varies as exponentially. When C greater than 0 and S equals to 0, T equals to T naught e to the power S naught by C, T naught by e to the power S naught by C. The plot is shown in figure. 1 mole of an ideal gas with heat capacity CV goes through a process in which its entropy S depends on T as S equals to alpha by T, where alpha is a constant. The gas temperature varies from T1 to T2. Find A, the molar heat capacity of the gas as a function of its temperature. B, the amount of heat transferred to the gas. C, the work performed by the gas. Solution. Since the entropy depends upon the absolute temperature and is given by S equals to alpha by T, differentiating ds equals to minus alpha by T square into dt, or equals to T ds equals to dq equals to minus alpha dt by T. Now we have to calculate molar heat capacity of the gas for 1 mole of gas. Hence dq equals to n into c into dt equal to c dt. From 1 and 2, c into dt equals to minus alpha dt by t. Hence c equals to minus alpha by t. B, now we have to find heat transfer from equation 1. dq equals to minus alpha into dt by t. On integration q equals to integration dq equals to minus of alpha into integration t1 to tt dt by t equals to minus alpha into log t2 by t1. Modulus of heat transfer q equals to alpha log t1 by t2. Answer C. Now from the first law of thermodynamics, dq equals to d plus dw. Hence dq equals to hence q equals to dq minus dw equals to minus alpha log t2 by t1 minus cv into t2 minus t1 equals to alpha log t1 by t2 plus cv into t1 minus t2. Answer